Welcome. Accessory systems provide the benefits of comfort and convenience to the driver and passengers. The common accessories on today's vehicles include power windows and door locks, power seats and sunroofs, and cruise control systems. In this video, we'll look at the different types of accessories, how they work, and how to diagnose these systems when something goes wrong. After viewing this video, you should be able to describe the operation of a power window system, describe the operation of a power door lock system, diagnose a multiplexed electrical system, understand the operation of electric motors used in accessory systems, and understand accessory drive systems. Many of the common accessories use electrical motors to do work. The most common use of motors is found in the power windows, power seats, power sunroofs, power mirrors, and power door locks. Electrically, these systems all work the same, so we'll look at these topics as a group. As we saw in the earlier videos, all circuits must have a source of electrical power. A circuit protection device such as a fuse or circuit breaker, a switch to control the circuit, a load that uses electrical energy to do work, and a ground to complete the circuit. In this group of electrical accessories, an electric motor is used to do the work as the power is transferred through cables, cogged belts, or linkage to move windows, seats, and sunroofs. The motors that are used to move accessories are called permanent magnet reversible motors. Most permanent magnet reversible motors include permanent magnets, an armature with a commutator, and brushes. We know that if a loop of wire carrying current is passed through a magnetic field, the magnetic field around the wire and the magnetic field around the field coil will repel each other, forcing the loop of wire to turn. In a motor, many loops of wire are held around an iron core called an armature. The iron core helps concentrate and direct the magnetic lines of force in the armature. The loops of wire are connected at the commutator of the armature. Sliding contacts, called brushes, ride on the commutator to direct full battery current to the armature. A similar set of brushes is used to complete the circuit to ground. The direction that the armature turns depends on the direction of current flow. When the master switch for a power window motor is placed in the up position, current flows from the battery through the master switch, through the individual window switch, to the top brush of the motor. Ground is supplied through the bottom brush of the motor, through the individual window switch and the master window switch. When the master switch is put in the down position, the current path is reversed and the motor armature turns in the opposite direction. When an individual window switch is used, battery current flows directly to the switch, through the motor, and to ground through the master switch. Depending on the position of the switch, the armature of the motor will rotate either clockwise or counterclockwise. The armature drives the gears, cables, or rack that moves the windows up and down, or the seat and sunroof forward or backward. Power window drives can be a conventional window regulator that uses a pinion gear and sector gear to raise and lower the window. Power seats are typically gear-driven assemblies that use either rack and pinion or worm gear drive transmissions to move the seats up and down or fore and aft. Gear drives are preferable for power seats because the weight of the driver or passenger places additional stress on the motor and gear drives. Power sunroof systems typically use drive cables that are moved by the motor to open or close the sunroof. Electrically controlled mirrors use a switch that controls dual drive, reversible permanent magnet motors. Diagnosis of any electrical problem begins by verifying that the condition exists. then developing a sound diagnostic strategy to isolate the cause of the condition. Let's take a look at an example of a problem with a passenger side power window that doesn't work. We'll start by trying to operate the window with the master switch. Just as the customer says, it won't go down. Let's make sure the window lock switch is off and test it using the individual switch on the passenger's door. It still doesn't work. Let's look at the wiring diagram of the circuit. We can begin by testing the circuit at the circuit breaker. We can use a test light or voltmeter to test for voltage at both sides of the fuse. If we had voltage on one side of the circuit breaker but not the other, then we would know the fuse is bad. But as you can see, we have voltage on both sides, so the fuse is good, and we can eliminate that as the cause of our problem. We could also eliminate the circuit breaker as a cause by operating any of the other windows as current flows to all window motors through the same circuit breaker. In this case, the other windows work, so let's continue on. The window motor is behind the door panel, and the window switch is easily removed, so let's check the switch first. There are two switches that we have to test. The first is the master switch that controls all of the windows. To test the switch, we can use a test lamp. Connect the test lamp across terminals 1 and 2. The test lamp should be on. Our lamp is on, so put the switch in the up position. In the up position, the switch position is changed to complete the motor circuit to the ground. Our lamp should go out. It does. Well, we know the switch is okay in the up position, but the window won't go down. So let's check the switch in the down position. The test lamp goes out when we press the switch down, so that circuit is complete as well through the master switch. It looks like the master switch is okay. Let's check the switch for the window. According to the diagram, we should have voltage at terminal number 6. Let's make sure that the lockout switch is closed before testing. Okay, we have voltage at the switch. That means that we have a complete circuit through the circuit breaker to the switch. If we connect our test lamp across terminal 5 or ground and terminal 6, we should have a circuit and the lamp should light. Okay, the test lamp lights. That means the circuit to ground through the master switch is okay, as we've completed a circuit with our test lamp. Let's check the switch to see if the switch completes the circuit. With the switch in the up position, the circuit through terminal 7 is complete, and the lamp between terminals 5 and 6 should go out. Looks like the switch is okay in the up position. Let's put the light between terminals 6 and 7 and test the down position that uses terminal 5 to complete the circuit to ground. The lamp is on until we press the down switch. Our tests show that the switch for the passenger's door works. We know that the motor should work if we use jumper wires for power and ground directly to the motor terminals. Let's try that. With power and ground to the terminals, the motor doesn't turn. Let's reverse the connections to see if it works in the other direction. Same thing, it doesn't work. Replacing the motor should fix the problem. Remember to always recheck your work to make sure it fixed the problem. All right, the window works from the door switch. You can use a similar approach to check the operation of the seat, sunroof, and the power window motors. As you can see, an understanding of wiring diagrams and diagnostic procedures can make electrical diagnosis a snap. Power windows, sunroofs, and seats can have mechanical problems that cause them to bind, stick, or drag during operation. When you have a complaint with a window or sunroof that works slowly, you'll have to determine if the problem is electrical or mechanical. Mechanical problems can include window or sunroof channels that are dirty or contaminated and restrict the free movement of the glass. or they can be loose or worn gear drive mechanisms that don't efficiently transmit the power of the motor to the moving assemblies. In some cases, aligning the windows or adjusting the drive cables of a sunroof will take care of the problem. In most cases, the worn gear train components will have to be replaced to restore the operation to normal. Cruise control systems, also known as automatic speed control devices, allow the driver to set a cruising speed for long highway trips. Most cruise control systems on today's vehicles are electronically controlled systems that use a computer to monitor operating conditions and output signals to an actuator that adjusts the throttle position to maintain vehicle speed. The designs of the actuators vary, but most use a servo that reacts to changes in vacuum applied to the servo diaphragm to adjust the position of the throttle in response to a change in operating conditions. The primary input for the cruise control system is the vehicle speed sensor. The driver uses the set switch to set the vehicle speed, which is typically restricted to speeds over 30 miles per hour. The value of the speed sensor is captured in the memory of the electronic control module that operates the cruise control system. As the vehicle speed drops below the set value, the electronic control module energizes a vacuum supply solenoid to allow more vacuum to the servo. Supplying more vacuum will cause the servo to open the throttle plates more to increase vehicle speed. When the vehicle speed begins to climb over the set value, a vacuum vent solenoid is actuated by the electronic control module. The vacuum vent solenoid bleeds off vacuum from the servo that causes the throttle plates to close, thereby decreasing vehicle speed. The continuous application of vacuum and venting of vacuum maintains the vehicle speed. The control unit monitors the circuits of the following switches to ensure that all switches are in the proper position prior to engaging the automatic cruise control. Cruise control main switch, cruise control set cancel switch, clutch pedal switch for manual transmissions, inhibitor switch for automatic transmissions, stop lamp switch, and brake pedal switch. Let's look at an example of a cruise control system that won't engage. Let's start by road testing the vehicle to confirm the condition. We'll try to set the vehicle speed at several different speeds over 45 miles per hour. Just like the customer says, the cruise control will not set at any speed. Now let's look at the wiring diagram. We know that the cruise control's electronic control unit gathers input from the different switches prior to engaging cruise control. Some switches, such as the stop lamp switch and the inhibitor switch, must be open for the electronic control module to enable cruise control. While other switches, such as the main switch, set switch, brake pedal switch, and clutch switch, must be closed to allow the cruise control to operate. An understanding of normally open and normally closed switches is essential to diagnosing cruise control systems. We also know that the switches are inputs to the electronic control module. That means that we can test all of the switches at the control unit. Remember, we can't use a test lamp on an electronic control unit or we'll damage the sensitive circuits. So we'll have to use a digital multimeter set to the volts test. Testing an electronic control unit for voltage requires that the terminal connector remain in place. Otherwise, we'll have an open circuit with no current flowing. Without current flowing, we can't check for voltage. To prevent damage to the control unit terminals, we'll use T-pins to back probe the terminals in the connectors and hook our meter probes to the pins. We can test the individual switches by testing for the presence of voltage or for the absence of voltage between the switch terminal and the ground terminal of the electronic control unit. The repair manual will identify the terminals for the different switches and the ground terminal of the electronic control unit. Our repair manual tells us we should have battery voltage from the main switch when the ignition key is on and the switch is turned on. We can connect our digital multimeter between the terminal for the main switch and ground at the electronic control unit and read the voltage. And we have battery voltage, so we know that circuit is okay. We should also have battery voltage at the terminal for the set switch when the switch is held in the on position. Let's check between that terminal and ground. We have battery voltage. That means the circuit on the set switch is okay. The wiring diagram tells us the brake cancel switch is normally closed, meaning we should have battery voltage at the terminal for the cutoff circuit. Our reading is 0 volts. That means the brake switch or the brake switch circuit is open. An open in that switch or circuit has the same effect as stepping on the brake pedal. The cruise control will not engage. Let's test the switch. We can use the ohm meter function of the digital multimeter to test the switch. If we test the switch at the connector, we should have continuity with the brake released, and no continuity with the brake pedal depressed. As you can see, we don't have continuity in either position. Let's disconnect the connector and test the switch. We have continuity with the brake pedal released, and no continuity with the brake pedal depressed. That means that the switch is okay, and our problem is in the connector. There it is. The mating pin for the switch has pulled back. We can repair the terminal and recheck our work. Looks like that fixed the problem. You can use these troubleshooting techniques when testing any system that uses an electronic control module. Always test the circuits at the electronic control unit by back-probing the terminals to see the values that the control unit sees. Then isolate the parts of the circuit to get to the cause of the problem. In this video, we've looked at some of the common accessory systems that use motors and how to diagnose these systems. Then we looked at electronically controlled accessory systems and how to test the inputs and outputs to determine if the circuit is operating properly. Thanks for watching.